So our next speaker is Alex Rice from Millsaps College, who will be talking on the sum product problem for small sets.
Thank you very much, Gene, and thanks to all the organizers for the invitation and the opportunity. Third time speaking at this particular conference, and the first two times I talked about what I normally talk about, which is Fourier analytic methods in additive combinatorics. And so if you've seen me talk before, it probably involved some ugly exponential sums and lots of iterated logarithms. That's not what I'm going to do today. Instead, I'm going to talk about some work that I did in the most recent iteration of a summer research program that I do with undergraduates at Millsaps College, which is a very small liberal arts college in Jackson, Mississippi, which is just about 2.5 hours or so north of here. So here's kind of the central problem. If you have a set of numbers, you can look at its sum set and its product set. So that's basically what it sounds like. The sum set is all the pairwise sums, including adding an element to itself. And the product set is all of the pairwise products. And so in these two examples here, these are both 4-element sets. And if you look at the sum set of A, you have these 9 elements, right? 3 plus 3 is 6, all the way out to 8 plus 8 is 16. Okay. The product set happens to also have 9 elements, right? From 3 times 3 equals 9, all the way to 8 times 8 equals 64. Now with B, there are 10 different sums, but only 7 different products. Okay, and if you look at this and play around with it, you sort of see what's going on, right? The reason, first of all, why does this have 9 and not 10? Well, it's because 4 plus 8 is the same as 6 plus 6. So there's a repeated representation there. So the number of distinct elements is 1 less than it could be. And that's why B times B has so few elements, right? Because there's lots of repeated products amongst these powers of 2. 1 times 8 is 2 times 4. 2 times 8 is 4 times 4, etc. Okay. So just as a starter fact, pretty quickly, the biggest that these could possibly be and the smallest that these could possibly be. So the smallest, B times B is an example of the smallest that it could possibly be, which is 2k minus 1, where k is the number of elements of A. And that equality only holds for some sets if your set is precisely an arithmetic progression. And it only holds for product sets if your set is precisely a geometric progression. Okay. On the other side, B plus B has 10 elements here, and that's because every possible way that you could get a different sum, you do, right? In other words, the only repeated representations you get are by flipping the order of the addition. So all that number on the right-hand side is exactly the number of unordered pairs in your set. So that's always going to be an upper bound. And at least in the sum set case, in the addition case, such a set is called a CDON set, and there's a huge literature just dedicated to those things, to sets in the integers or in a group where adding 2 elements always gives you something different other than just swapping the order. Okay. So what is the sum product problem? So can the sum set and the product set both be small at the same time? Okay. Where what I mean by small is like noticeably smaller than that maximum. Okay, so to make this more official, here's a definition. So fix the size of the set. So K is the size of the set. Then look at every possible choice of K positive integers. And for each of those choices, take the larger of the 2, right? So you want to minimize that maximum, because what you really want to ask is, how small can I make both at the same time? Okay. So just based on that starter fact from the previous slide, because these things are always between 2k minus 1 and k squared plus k over 2, this minimax is certainly at least linear in K and at most quadratic in K. So the question is, what is the truth in terms of order of magnitude, right? So this was introduced just over 40 years ago. And while I haven't done any work on it directly until now, I would say this has been the biggest question in additive combinatorics over that time, over the last 40 years. So the question is, how does this grow as a function of K? Is it linear? Is it quadratic? Is it somewhere in between? So here's what's known. For an upper bound, it's not quite quadratic. In other words, it's bounded by above by k squared over a small power of log k. Okay, so it's little o of k squared. And the way that you can get that is just take a to be the first k numbers. And then that has very few sums. It has 2k minus 1 sums. So then the question becomes, how many products does it have? And my students really liked this part because then it becomes kind of a question you could explain to a fourth grader, because it is a multiplication table. It is how many numbers can be written as a number between 1 and k times another number between 1 and k. So you're counting the number of distinct products in the k by k multiplication table. And it turns out that there are fewer distinct products than you might guess. It might not jive with your intuition that that is little o of k squared, but it is. That means as k grows, the number of repeats in your multiplication table starts getting really, really, really high. And so this estimate, I would say the most precise estimate for the multiplication table problem is due to Kevin Ford. And the conventional wisdom now on the sum product problem is that this is actually close to the truth. They do think that this function SP of k is at least like k to the 2 minus little o of 1, okay? But proving that requires proving an upper bound all the way to that point. And that's what's turned out to be really hard, okay? Erdős and Semeretti proved, okay, it's definitely not linear. You can definitely get a positive constant improvement. But after that, I would really encourage everybody to take a look at these two papers. They're really short and they're really magical, because what Elekesh and Cholomoshi were both able to do is cast this problem from sort of additive combinatorics into incidence geometry, where the product of the size of the sum set and the size of the product set can be thought of as the number of incidences between points and lines in the plane. And it's really remarkable how easily they get these results on something that people have thought about for a long time. But hasn't been much movement since then. The current record, which is also just refinements over these incidence geometry methods, is k to the 1 plus a third plus 2 over 1167. So that's the current record. That's due to Misha Rudinev and Sophie Stevens. Okay. And again, the conjecture is that this delta can get arbitrarily close to 1. Now, if you moved that even a little, that would be a big deal. But I had 5 undergraduates at a tiny school in Jackson, Mississippi. So the goal was not to move this. The goal was to just look at this from a little bit of a different angle to get kind of some low-hanging fruit. And so the different angle I took was, well, instead of thinking of k growing to infinity, what if you could just get the exact answer for small values of k? Like, what if k was 8 or something? And how far could you push that, and how would it all work? So this is what we were able to do. We were able to get the exact answer up to k equals 9. And what we have here are examples. So technically, these examples only show you the upper bounds, but we were also able to prove the corresponding sharp lower bounds. So just looking at k equals 9, that is a set of 9 positive integers with exactly 25 distinct sums and exactly 25 distinct products. And what I'm telling you is you could pick any 9 positive integers in the world, and at least one of these two sets would have at least 25 elements. Okay. So in terms of making both of these small at the same time, that is literally the best that you can do. Okay. So how does that work? And these are all sharp examples for k equals 4 through 9. 2 and 3 are trivial if you think about it a little bit. Okay, so we used some older classification theorems of Freiman, who is kind of the grandfather of this field of sort of inverse problems for set addition. You know, what I mean by inverse problems for set addition is, you know, that if you have an arithmetic progression and you take its sum set, it's really small. He was the first person to ask, well, but if I take my sum set and it's really small, does that mean my set looks like an arithmetic progression? Okay. And this was the first kind of big theorem of that type, which says that if the sum set is close to its minimum, in the sense that it's less than or equal to 3k minus 4, then it has to be pretty sharply contained in an arithmetic progression. So one approach here is to say, okay, if my set has less than or equal to 3k minus 4 elements, it has to be contained in this arithmetic progression. Can I then use that structure to prove that it has to have a lot of products, or at least the number of products that I want? So in other words, what does the product set of a dense subset of an arithmetic progression look like? Okay, so an arithmetic progression looks like this. And if you could prove some bounds independent of x and d is really what you want. And if you look at the way a product of those two elements, the way products of those elements look like, then, you know, the problem is for different choices of a and b, this might wind up being the exact same thing. You might get repeats. But as long as you have a pair where one of a plus b and a times b goes up and neither of them go down, then you know that you can build a strictly increasing sequence of products. And so this is just one diagram of an example of a 6-element subset of a 9-term arithmetic progression. And you're finding a chain that corresponds to a strictly increasing sequence of 15 products. Okay. So if you think about it, you could just do that by hand for every possible choice of 2k minus 3 elements out of, of k elements out of 2k minus 3. If you add up all the cases, there are 285 of them. You know, it's possible that one could have written a script to do this, but that's not what we did. My students did all 285 by hand, just like this. Okay. Okay, but there's another approach that's just a little bit more heavy duty. I mean, not much more. It uses the idea of Freiman isomorphism, which in particular relies on the classification of finitely generated abelian groups. It basically says that for finite sets, the addition, the multiplication structure of any given finite set of positive numbers is equivalent to the addition structure of some other set of numbers. And so in other words, the conclusion that you get for arithmetic progressions in the additive case, you can also get it for geometric progressions in the multiplicative case. And so if instead you make your first assumption that the set has very few products, it's actually much easier to then leap to the fact that it has a lot of sums. And that's because geometric progressions always have a lot of sums. In fact, they're always seed-on sets if you're sitting within the positive integers. If you allow for negative common ratio, for example, well, it's the one example, r equals -2, you don't get a seed-on set because -2 plus 4 is 1 plus 1, so you do get a repeat. If you aren't working in the integers and your common ratio can be irrational, you also don't necessarily have a seed onset. Oh, whoops. 1 plus phi cubed is phi squared plus phi squared, where phi is the golden ratio. But again, we're working over the natural numbers, so neither of these counterexamples are a problem. So that gives it to us to say that this SP of k is always at least 3k minus 4. But when you get into higher k, 3k minus 4 isn't the answer anymore. You can find counterexamples. So what if it goes up to 3k minus 3? Freiman has a theorem for that too. And it gives you these two cases. Either you're contained in a geometric progression if you have that few products, in which case you're done, because the geometric progression is a seed onset, so you automatically get lots of sums. But then there's this other really annoying case. It's a union of two separate geometric progressions of the same common ratio. So that forces you to look at, if I have two separate geometric progressions of the same common ratio, how many different sums can I have? Or can I get a lower bound on the number of sums? And so that's sort of the last remaining case that we had to work really hard to work with. So let's say you have a union of two geometric progressions with the same common ratio. By the inclusion-exclusion principle, you can get a lower bound for the size of A plus A by looking at B plus B, C plus C, and B plus C, and then subtracting all the intersections. That will give you a lower bound on the size of that set. But B and C are geometric progressions. So they're seed onsets, so you know exactly how many elements there are in B plus B and C plus C. And then you can work with B plus C and the intersections. And you might like to say that these things don't overlap, but they do. And that's what this picture shows. So what in the world are these arrows? 8 plus 16 is 12 plus 12. 12 plus 24 is 18 plus 18. 18 plus 36 is 27 plus 27. Notice those two lines are both geometric progressions with common ratio 3/2. So you do get overlap, which could cause a problem. But it turns out that those overlaps are limited themselves to a single geometric progression. So notice the elements in the overlap here are 24, 36, 54. It's that single geometric progression with common ratio 3/2. And because of that, you can get an upper bound on the size of those intersections. And so this is what you get. In this case, if m is the number of elements in the first piece and n is the number of elements in the second piece, you get the maximum size of A plus A minus the size of these potential overlaps or repeated representations. But notice the leading term here is quadratic and all these terms are linear. So for k at least 7, you always get what you want, which is that the number of sums is at least 3k minus 2. You do have to treat the case r equals 2 separately, but in that case, the elements grow fast enough so that everything works out. So then the question is just, can you push this any further? I mean, maybe, but I think it's going to actually be to even go one step further. I think it's going to be really hard. This is our best guess. These are 10 elements, and this set I think has like 29 sums and 30 products. And every other example we checked, at least one of the two sets had at least 30 elements. But to prove SP of 10 equals 30, you have to consider what happens if a set has exactly 29 products or exactly 29 sums or even fewer. The problem is there are no existing classification theorems that tell you at all what a set like that has to look like, at least not with explicit bounds, right? Of course, there are these big picture theorems of Freiman and all these things that have come after it, but all of those theorems have implied ineffective constants, so that's not going to help here. So you would really have to get your hands dirty and say, if a set had like 29 products, what does its structure have to look like? And so far that is not really known at all. So maybe maybe some work for the future. So I'll stop right there.
Thank you. Are there any questions for?
Yeah, sure.
Oh, I just wondering, did you also keep track of any of the difference sets, note to see if any of the differences were smaller than the sum set? I'm just curious. Okay. I guess a follow-up question. Did you notice, because you probably ran a lot of numerical calculations, did you notice any patterns in like these example sets that
To that sort of fit into the umbrella of Freiman's classifications. And as soon as you can't, so I would say the only numerical calculations we did was to see if we could beat 30 for k equals 10. But maybe to answer your question, I am certainly not claiming any sort of uniqueness for these examples. And I do not know, I mean, there are some things that are pretty clear, like you want to like keep the set of prime factors relatively small, like it's clear, like I'm skipping 5 and 7 here, things like that. So I would say the patterns are, how can you maintain efficient containment in like density or efficient containment within an arithmetic progression while limiting the number of distinct prime factors?
Thank you.
Yep. Information about the number of sums, you would then want to show that no such set exists at all, right? Like, so I would say no, there's nothing explicit beyond 3k minus 3 at all. You know, there are all these big theorems like, if the size of a plus a is less than or equal to c times the size of a, then a is contained in a generalized arithmetic progression of density e to the implied constant times, right? So everything's very asymptotic and sort of ineffective.
Yeah.
I haven't even published something for 3k minus 2, and it was found pretty quickly to be wrong. So even just 3k minus 2 is single operation. So I don't know that you could really try to prove a classification with information from both operations at the same time, which I think is what you're asking. But it's a very interesting question, but there's nothing that I know of to that effect. Yeah.
Okay, I get all that. Yeah,
Sure.
So just looking at those sets, is it known that like just like some integers up to some bound with some like smoothness bound, just is it known that something like that doesn't beat just like the integers?
Yeah, so
1 to
if you just look at
yeah.
the set of, I think if you big picture, if you just looked at the set of smooth numbers, that you would be able to prove it, that eventually those sets had too many sums, right? Because smooth numbers would behave well under product sets. And so I think you could probably, I don't know for sure, but I think you could probably prove a lower bound on the size of the sum set for a set like that. By the way, another question that I was asked by Pete Clark at UGA recently is this function SP of k even like algorithmically computable in any way? And I think that's a fun question to think about, right? Because you're asking a question about all choices of k element subsets of the natural numbers. So you would have to prove something that in some way limited that to a finite computation, and it's not clear to me how to do that at all. So I would say currently this arithmetic function has no algorithmic runtime at all.
You might be able to use the fact that primes get really sparse if you consider numbers that are too large, and you want to kind of effectively fit as little distinct primes in there as you want. So you might be able to use some argument of like, well, we don't want to consider too large numbers because then the multiplication, the size of the product gets too large.
Yeah, I mean, I encourage you to try something like that. Yeah.
Are there any other questions for a speaker? Yeah. All right. Let's thank Alex again.